Welcome back, dear students, to the tetrahedron chemistry classes. In today's class, I am going to discuss enthalpy or the heat of the formation, which is the very basic topic of the thermochemistry. And heat of formation is very important for you to calculate the standard heat of the reaction and heat of combustion and many other things, right? So first of all, what is heat of formation? This is the definition: the change in the enthalpy that takes place when 1 mole of the compound is formed from its constituents elements. So see guys, if you are in 11th class and you don't have any idea about the enthalpy change and the heat change, so this may confuse you whether we can call it as enthalpy change or the heat change. So I'm telling you, enthalpy change is more common because it is because enthalpy is the thermodynamic term and it is a state function, right? And all the state functions cannot be calculated exactly, only their difference can be calculated. So whenever you deal with the enthalpy change, it simply means you are dealing with the delta H, right? Where H is the symbol for the enthalpy and delta is the difference between the final and the initial state. Okay, this thing you should know. And in this particular topic or in the upcoming topics as well, we will focus only on the enthalpy change but not directly on the heat change. Okay, so what will happen whenever you take your constituent elements and from these elements you form 1 mole of the compound, whatever the heat change will be there, this is called your heat of formation. Okay, for example, say you are having iron and it is in solid state. It is very important for you guys to write the state of the metals, gaseous products, all these things, right? Because these states are very important, because standard heat of formation is different for the different states of a particular compound. Say for example, what for liquid water, standard heat of reaction is different, sorry, standard heat of formation is different, right? And for water vapor, the value of the heat of formation is different. That's why it is very important to write their states as well. Okay, and you are reacting this iron with the sulfur, and sulfur is again solid. Okay, and I'm writing only S for this one. I am not writing the polyatomic sulfur like S8. Okay, because I'm going to form this particular compound which is known as FeS, right? And you are forming this FeS, and this FeS is also solid. So what you are doing here, you are taking your pure iron and pure sulfur and you are reacting them together to produce this FeS. And in this particular reaction, the enthalpy of formation delta H, and if you write F in the subscript, it shows the formation. F stands for the formation, and the value for this particular reaction is 24.0 kilocalories. Okay, and then say for example, you are having your another compound. Say you are having this carbon, and this carbon is reacting with the hydrogen gas, for example. Okay, and it is forming, say, acetylene gas, C2H2, right? So you know your carbon is solid, your hydrogen is gas, your acetylene is gas. Okay, so you are forming 1 mole of acetylene. For the formation of the 1 mole of the acetylene, you will need the two carbons, 2 moles of the carbons. So what you will do, you will write 2 of carbons here. Now you can see 2 carbon and 2 hydrogen on the left hand side in the reactant side, or in the product side also you are having the 2 carbon and the 2 hydrogen, and this is in the carbon is in the solid form. Basically it is in the graphite form. Okay, and your hydrogen is gas and this acetylene is also gas. And for this particular reaction, enthalpy of formation, which is known as the delta HF, is different, and the value is plus 53.14 kilocalorie. So why I have taken these two examples? Because I want to give you an idea that your enthalpy of formation may have the negative sign or it may have the positive sign depending on the type of the reaction. I hope this is quite clear to you, right? Now moving further, so this is your basically heat of formation. Now the next thing is the heat or the standard, and now I'm talking about the standard enthalpy of formation. So when I say the standard enthalpy of formation, so we'll denote this as delta H standard F. See, when you put not or the small zero as a subscript, as a superscript on any particular thing, then it is in chemistry it shows the standard form. Okay, so this standard enthalpy of formation is exactly your enthalpy of formation. The only difference is that you will form your compounds in the standard states. And what is the meaning of the standard states? 298 Kelvin, right? That is your 25 degrees centigrade and 1 atmospheric pressure. When you are doing your reaction on in these conditions, then whatever the enthalpy change will be there for a particular kind of the reaction, this is known as the standard enthalpy of formation. So the definition remains same. The change in the enthalpy that takes place when 1 mole of the compound is formed from its constituent elements, all substances being in their standard states, which means that at 298 Kelvin and at 1 atmospheric pressure, you are doing your reaction. Okay, and how we can calculate the standard enthalpy of formation? There is a quite straightforward formula for this one. Say your delta H standard, you can write in that manner. This is equals to what? This you can write as delta H standard formation for the products. That means the compounds present on the right hand side of the equation. Okay, minus standard enthalpy of formation for the reactants. See, it is very, very important for you to write the things in the say very clear manner. Okay, so that your teacher can easily understand what actually you have written over there. Okay, you cannot use the shortcut types of the things, and you see the work which looks untidy, right? So this is one way of writing this particular formula. Delta H standard equals to sum of delta H this here F, and in the bracket that is P, and then you are having delta H standard F of your R, and again it is the summation. Okay, sum, that means sum of the standard enthalpies of formation of all the products minus sum of the standard enthalpy of formation of all the reactants. So this is the table which gives you the information about the standard heat of formation of some compounds. Like as I already told you, see, for water when it is in vapor state, your standard enthalpy of formation is minus 57.84 kilocalorie per mole. Okay, and when this water is in the liquid state, then this value actually is minus 68.38. Similarly, you can see the values of the different compounds. However, you don't need to memorize all these values. In the examination, these values will be given to you, right? So by convention, the standard heat of formation of all the elements is assumed to be zero. So in the thermochemistry, whenever you are say whenever you have the elements, right? So elements will not have any standard enthalpy, right? The standard enthalpy for the elements conventionally actually it is assumed to be zero. However, it is not zero, but for the calculation for the pure elements, it is taken as zero. It is very, very important. Okay. Now you can see this is the question which will solve. Calculate the uh, enthalpy change for the reaction. Reaction is carbon dioxide in the gaseous state reacting with the hydrogen gas, producing carbon monoxide in the gaseous state and the water in the gaseous state. Given that standard enthalpy of formation for carbon dioxide, carbon monoxide H2O minus 393.5, minus 111.31, and minus 241.80 kilojoule per mole. Here, this question used a different unit. Earlier, you can see here, we are talking about the kilocalories per mole, but here the question gives the value in the kilojoule per mole. It will not make any difference, right? You have the different units in the different types of the questions. So how we can solve this particular question? Standard enthalpy of reaction equals to standard enthalpy of formation for the products minus standard enthalpy of formation for the reactants. Of course, If you want, then you can put summation here as well. Okay, just like that. So what the equation will become now for this particular specific case, say this is your bracket, delta HF standard for in the product side. Your product are carbon monoxide. So this is CO in the gaseous state, bracket close, plus your second product is H2O in the gaseous state. So you'll write delta H F standard for H2O gas. So this is for your products, and then minus for the reactants, which is your delta H standard F for carbon dioxide, okay, in the gaseous state, plus delta H standard formation for your hydrogen gas, right? So why I have written this long equation here, right? It is very, very important for the beginners to write each and everything precisely, because this is very important. It will be very, very important for you when you solve the numerical based on the Hash law. Okay. So this is the bracket for carbon monoxide. The value is minus 111.31. Okay. Plus, and the value for your water is minus 241.80, minus 241.80. So this is all about your products, bracket close, minus, now reactant for carbon dioxide. You see the value is minus 393.5. So we'll write here minus 393.5 plus for hydrogen, it is pure element. It is in elemental state, right? It is not a compound. It's a simply element, and by convention for the elements, this standard enthalpy of formation we assumed as 0. So you will write the 0 here. This will become minus 111.3 minus 241.80, and then your minus minus will become plus. So this is 393.5, and this will be equal to minus 353.1. Let me check. Yes, 240, 250, 250. Yes, 253.1 plus your 393.5, and finally you will have your answer. That would be your 40.4 kilojoule. This is for the reaction. Okay, this is for the entire reaction. So you cannot write the per mole here. And this is my next numerical. Okay, what it says. The standard heats of formation of ethanol in the liquid state, carbon dioxide in the gaseous state, and water in the liquid state are minus 277.0, minus 393.5. This we have already seen in the previous question, and then minus 285.5 kilojoule per mole respectively. Calculate standard enthalpy change for the reaction ethanol reacting with the oxygen producing carbon dioxide and your water molecule. So again, it's a quite straightforward and simple thing. What you will do here, I'm writing solution. So your delta H for the reaction would be equals to what? You see, product are your carbon dioxide and water, and you know carbon dioxide, 2 moles of carbon dioxide is present here. So you will multiply the value of the standard heat of formation of this carbon dioxide with 2. So 2 multiplied by minus 393.5. See, in the previous question, I have written this particular long equation, but here I skip that particular point. I am straightforward writing the values and doing the calculation. What you can do for your practice, you can write the entire equations here as well. Okay, so this is 2 into minus 393.5 uh, bracket close, plus your second product, which is your water, and 3 moles of the waters are there. So this value multiplied by 3, 3 multiplied by, and for the water the value is your this 285.5 minus 285.5. Okay, this is all about the product. Then minus reactants, and for reactants your one molecule of ethanol is there, and for ethanol the value is minus 277.0, and plus 3 moles of oxygens are there, but the value is 0 for this one. So 3 multiplied by 0, that will give you the 0. So if you solve this thing further, so what you will have here, you will have minus 1643.5. So you multiply 2 with this one and then 3 with this one, and then you add both of them together to get this particular value, and then you are minus 277.0. This is basically your minus 1643.5 plus 277.0, and this will give you minus 1366.5 kilojoule. Okay, so this would be your answer. So this is basically the concept of the heat of the reaction, or standard heat of the formation, especially in terms of the enthalpy, because enthalpy is more fundamental in the light of the thermodynamics. And remember, it's a state function, so we cannot determine the exact value of this one. We can only we can only determine the, or calculate the difference between the initial and the final stages of the enthalpies. Okay, so this is the very basic thing. In the next class I'll continue with the some other topic, of course, of thermochemistry. Okay, so that's it for today. Thank you.